Okay, in this section, we are going to go over exponential applications. And exponentials are something that we start as early as Math 1. So some of this is stuff that you have probably seen before, but we probably could use a refresher on it as well. So the general form for an exponential equation is y equals a times b to the x power. And a in this situation is your principal or your starting value. And b is your growth or decay factor. So if you have exponential growth, then that b is going to be 1 plus the rate as a decimal. So if you have a growth rate of 5%, then it would be 1 plus 0.05. Your decay, if you have decay, then that b is going to be 1 minus the rate. So, for example, a decay of 5% would be 1 minus 0.05. So this is how you set up exponential equations. Now, here I've got 4 exponential equations that are already set up, and we need to decide whether we're talking about growth or decay and by what percent. So, in general, if you're talking about growth, then your b value, this value right here in the function, is going to be greater than 1. So we do 1 plus the rate, so it's going to be greater than 1. So we can see this first equation right here would be a growth. And to find the rate, you want to find the difference from 1 that you have. So I'm going to do 1.05, and I'm going to subtract 1, and that gives me 0.05. Rates, typically, we like to give those as percentages. So this is the decimal. To turn this into a percent, we're going to move that decimal place 2 places, and we'll get 5%. So this particular equation would be 6,000 of something growing at 5%. Let me change this so it fills up the screen a little better. All right, for example 2, we've got f of x equals 3 to the x power. These can be really tricky because here we do not have an a value. So if you don't have an a value there, it's like you've got 1 times 3 to the x. So that 3 is your b in this case. So 3 is larger than 1, so this is going to be growth. And then you want to see the difference from 1. So I'm going to do 3 minus 1, which will give me 2. Now that is a decimal, although it doesn't look like it. It's not 2%. I've got to change this to a percent. So I'm going to move that decimal place 2 places to the right. I'm going to fill it in with zeros. So I've got 200%. So this is a 200% growth in this particular case. For example 3, I have my b value is 0.98, and 0.98 is less than 1, so I'm going to be talking about decay here. And we can do the same thing we've been doing for these other problems to find that rate. We can do 0.98 minus 1, and that is going to give us negative 0.02, and that negative lets us know that we're dealing with decay here. And so I can move my decimal place 2 places to change this to a percent, and I'm going to get 2%. So we're talking about a decay at 2%. For example 4, here 1/2 is my b value. So 1/2 is also less than 1, so this particular equation is going to model decay. And I can do the same thing I've been doing. 1/2 minus 1 is going to give me negative 1/2. That negative right there lets me know we're dealing with decay. And let's just change this to negative 0.5 and then move our decimal 2 places, and we'll get 50%. So this would model something that's decaying at a rate of 50% per time. Okay, now let's look at building some equations from situations. So we're going to start with just some compounded interest. So for example 1, you invest $6,000 in an account earning 5% APR compounded annually. How much money will be in the account in 5 years? So this APR is your annual percentage rate, and so we're dealing with an annual percentage rate, and we are compounding annually. So as long as those match, it's going to be a fairly straightforward problem. So it says how much money will be in the account in 5 years. So we're doing y equals a times b to the x. A is your principal. It's what you start with, which in this case is 6,000. And your b value, to find that b, you're going to do 1 plus 0.05, because 0.05 is the decimal for 5%. And so your b value is going to be 1.05, and to the x power right here. And that x right there stands for years, because our interest is compounded annually. So if we want to know the amount of money in the account in 5 years, I'm going to make this a little bit smaller, and we don't need that. And I'm going to go to Desmos here. Let's see if I can make this show up like I want it. Let's see. And I'm going to make this a little smaller so it'll show up. Okay. And so all I've got to do here is plug in 5 for that exponent. So I'd have 6,000 times 1.05 to the 5th power. And here I'm going to get for my answer $7,657.69. In this particular case, we're going to round to the nearest cent here. So that is the amount that you would have if you invested in this particular account. Now, let's also talk about what happens if we have the exact same situation, but we're compounding our interest monthly. So that means instead of adding your interest back to your principal once a year, they're going to do that monthly. So this means here that we've got 5% APR, annual percentage rate, but that is not my monthly percentage rate. They're not going to give you 5% every month. If they did, if you find a bank that will do that, go there, because you're going to make tons of money, but they don't. So what we have to do here is we've got to divide this by 12 to change it to a monthly interest rate. And so if we do 5 divided by 12, we're going to get 0.416 repeating percent, and that is your monthly rate. Okay, so instead of using 1.05 like we did on the last problem, our equation is going to look like this: 6,000 times 1.00416 repeating to the x power. And so here, remember, it's a little bit confusing sometimes when your rate is already a decimal, but you still got to move it 2 places to turn it to a decimal and put those zeros in there. And what you have to know here is that this particular account compounds monthly. So that means your time right here is in months, not years. Here we were compounding annually, so our time was in years. This time we're compounding monthly, so our time is in months. So whenever we plug a number in for x, we're not going to plug in 5, because if we plug in 5, that would be for 5 months. So in this case, we want to know 5 years. So we've got to do 5 times 12, which is 60. And so we are going to type in 6,000 times 1.0041. I'm going to put a lot of 6's here, to the 60th power, because there's 60 months in 5 years. And you can see here that this time we are going to get $4,700.15. So you can see we've got a difference of about $40 here. So it's $40 over 5 years. It doesn't make a huge difference. But if you're going to have the ability to get your interest compounded monthly rather than yearly, you would always want to do that because it will earn you just a little bit more money. Okay, let's look at the next problem that we've got here. If Alfredo invests his money in an account that gets 4.8% APR compounded quarterly, how long will it take his money to double? So this particular account is compounding quarterly, which would mean 4 times per year. And that means we're going to have to take our 4.8% and we're going to have to divide it by 4 to change it to our, because this is annual percentage rate, we're going to have to divide it by 4, which is going to give us 1.2%, and this is your quarterly rate. Now, this equation, or this problem, is a little different than the last one that we looked at because in this problem, we are not given a principal amount. It just asks about how long it will take his money to double. So since I don't know how much money Alfredo has, I'm just going to guess right here. So I'm going to say that Alfredo has $1,000. So I'm going to make my equation y equals 1,000 times 1.012 to the x power, and because we're compounding quarterly here, that x is the number of quarters. And so here, of course, too, we had to move that decimal 2 places, so we had a decimal to add to our 1. So this would be our equation. Now, this is where our logarithms are going to come in a little bit. If we want to solve this, and I want to solve it precisely, you could type it into a TI 84 and look at the table and get a good idea, but I want to solve it precisely. So if Alfredo started with $1,000, I want to know when he'll end up with $2,000. And so I'm going to plug in 2,000 for this y because that y is the amount of money that's in the account. So I'm going to do 2,000 equals 1,000 times 1.012 to the x power. And so I need to solve this equation for this x right here. The first thing I'm going to do is get rid of this 1,000 by dividing it off. So I get 2 equals 1.012 to the x power. Now what I need to do is I need to undo this 1.012 to the x. So in order to do that, I'm going to do log base 1.012 on both sides. And so the log 1.012 and the 1.012 raised to the power, they're going to cancel each other out here. And so I'm just going to be left with an x on this right side. And my answer is going to be log base 1.012 of 2. And we can type that into Desmos really quickly over here. So functions log 1.012 of 2 is going to give us 58.108. Here, and remember that our x here is in quarters. So this is quarters. Now typically we don't list how many quarters of time that we're going to have unless it's less than 4. So here we wouldn't really want to give this as our answer. What we would want to do is we would want to take this answer right here and divide it by 2. And so if we do, not 2, there's 4 quarters in here, divide it by 4. So this would be 14.527 years. So that's how long it would take for Alfredo's money to double. Now, I just made up the fact that Alfredo had $1,000. Alfredo might have $10,000. He might only have $1. Let me show you that it really doesn't matter. Let's go with that most simple situation. Let's pretend Alfredo only had $1. So that means our equation would be 1 times 1.012 to the x power. And so if Alfredo starts with $1, then that means if it doubles, he has $2. And so if I'm solving this equation, the first thing I'm going to do is divide off that 1, kind of. I mean, really, it's just 1 anyway. But I would have 2 equals 1.012 to the x power. Notice, that is exactly what I had right here. And the rest of the solving process is going to be the same. What if Alfredo had $50? Well, if he had $50, then our equation looks like this. And to double that money would be $100. And so if we divided off that 50 to solve, 100 divided by 50 is 2. So we'd have 1.012 to the x. Notice, same thing we had right here, same thing we get over here. So you're going to get the same answer no matter what amount of money you say that Alfredo has. All right, let's continue on. Now, the first ones that we looked at were dealing with compounded interest, but there is another type of compounded interest that is used often, and that is continuous compounded interest, or it also continuous growth and decay can also be used quite frequently for population growth. And so in this equation, you'll have A equals PE to the RT. P stands for your principal amount here. It's like your A in our other exponential equation. E is a fixed number. It is 2.718281, so on. It's kind of like pi. Pi is always 3.14159. And so this is a fixed number. Even though it looks like a variable, it is a number. R is your rate as a decimal, and T is some sort of amount of time. Okay, so let's look at how we could use this equation. Walter just got a job as a high school chemistry teacher. His first year, he lives with his parents, and he saves $20,000. He puts the money in an account that earns 6.75% interest compounded continuously. If he leaves the money in the account without making any deposits or withdrawals, how much money will be in the account when he retires 29 years from now? So he saves $20,000 this very first year, and he is getting interest compounded continuously. So that should tell us we're using A equals PE to the RT. So our amount is going to be our principal, which is $20,000, E to the rate, which is going to be 0.0675. Make sure you change that to a decimal, times T, which is time here. And in particular, that time is going to be our years. And I probably did not word this problem well enough, but that would be your annual interest. Now, we are compounding continuously, but in this compounded continuous formula, our interest rate, if it is an annual interest rate, then the time is going to be measured in years. So all we need to do is plug in a 29 into this equation. So if I type that into Desmos, 20,000 E to the 0.0675 times 29 is going to give us $141,632.02. So if Walter was able to do this and able to find an account that would give him that sort of interest, then he would turn his $20,000 into $141,000 in that time, and he wouldn't have even had to sell math and quit his job as a teacher like Breaking Bad. So there's our answer to that problem. Okay, here's our next problem. Jeffrey invests $4,000 in an account that gets 5% annual percentage rate compounded continuously. If he does not make any deposits or withdrawals, how long will it take for him to have $10,000 in his account? So we're going to set up our equation using that same formula. So we're going to have A equals, our principal is $4,000, and we'll have E to the, our rate is 0.05 T. And our question here asks us how long it will take us or take him until he has $10,000 in his account. So the thing that we're looking for here is that amount of time. We're not going to replace T in our equation. And our A right here, we know that's going to be $10,000. So we're going to plug in $10,000 equals $4,000. E to the 0.05 T. And we're going to solve this equation for our T right there. So the first thing we would do is we would divide by 4,000. So 10,000 divided by 4,000 is going to be 10 divided by 4, which is going to give us 2.5, I believe. Yes, so we'll get 2.5 equals E to the 0.05 T. And what we've got to do here, the inverse of an E is a natural log. So we're going to do natural log of both sides. And natural log and E will cancel over here. So we'll have natural log of 2.5 is going to equal 0.05 T. And so to solve for that T, I'm going to divide by 0.05. And I'm going to type that into Desmos over here. So natural log of 2.5 divided by 0.05 is going to give us a T of 18.326 years. So in this particular account, if you needed $10,000, it would take you 18.326 years to get that. All right, so that covers the types of problems that you're going to see in your assignment today. There is a worksheet there that has several word problems on it. You only have to do certain problems, so make sure you see the ones that you have to do there. Once you have finished doing those problems, please email me your work. Please at least show me your setup of your problem. So don't just write 1 is 2,534. Show me how you set up the problem on those. These don't have a lot of work to show, but at least show me how you set up the problem. Thank you for watching, and I'll see you guys tomorrow. Remember, tomorrow's meeting will be at 10:15 instead of 10 o'clock.